So this is a really interesting question from the Irish Maths Olympiad, and before I say anything more about it, I'll give you a chance to try it yourself if you'd like, and then I'm going to start talking about it. So in this question, you can kind of use inequalities to create equalities, which sounds kind of crazy, but it actually works out pretty well. And that kind of reveals a really interesting pattern in these peculiar numbers. So 1978 is peculiar because if you take the first two digits, 19, and add them to the last two, 78, you get 97, which is the middle two numbers. And then the question asks, when was the last peculiar year, and when will the next one be? So you could just try guessing them, but the problem is that the gaps could be pretty big, and then how do you prove that that's actually the one before 1978? So it's probably better to do a more methodical approach, which is what I'm going to show you. Well, I'm going to show you how I did it. So the first thing we have to do is we have to convert this into something that we can work with mathematically. So how do we represent a 4-digit number mathematically? Well, one way you can do it, and I think the only way, is you can write it as such. You can write it as 1000 A plus 100 B plus 10 C plus D. And I'll just finish writing this before I explain it. A, B, and C, and D have to be between 0 and 9. And of course, they are also whole numbers. They are integers. So the reason that we use this is because A multiplied by all of these digits will give 0, and then A times 1 is just A. So that'll put A in the 1000 place. And then B times the zeros is all 0, and then B times 1 will give us B in the 100 place, and so on. So this gives us a 4-digit number, and the digits are A, B, C, D. So we can now use this to kind of write down what the question is asking us. So what the question is asking us is it's going to be 10A plus B for those first two digits. And then we're going to have 10C plus D for the last two. And that's going to be equal to the middle two digits as a 2-digit number. So that's going to be 10B plus C. So this is kind of the equation that the question tells us is how it works. And what we can do is we can kind of simplify this. So I'm going to solve for D here, which might seem a bit arbitrary, but the reason I'm solving for D is because the rest of them have a coefficient in front. So, and you'll see why I solve for D now. I've obviously done this in advance, so I'm just trying to do it the fastest way. So if we solve for D, well, we end up with minus 10A on the right side. We have 10B minus B will give us plus 9B. Then we have C minus 10C will give us minus 9C. And we notice that these two have a 9 in common. And you might be stuck here in terms of what we can do. The only kind of other piece of information we have is we know that D is between 0 and 9, which seems kind of redundant. But then remember, see how we're multiplying by 9 here? If we could divide by 9, that might actually give us a good constraint. So let's try that. And obviously we're going to try D because we have D by itself. So we can say that between 0 and 9 is minus 10A plus 9B minus 9C. So when I was solving this initially, I decided I'll just make A equals 1 because we want to find the one before 1978 anyway. So it's going to start with a 1, obviously. So if we just write down A equals 1, then this A here is gone because minus 10 times 1 is minus 10, and as is this one. And now what we can do is we can add 10 across on this inequality. So I'm going to bring it down here, and we can say that 10, and then we have 9B minus 9C, and then 9 plus 10 isn't 21, it's 19. Unfortunately, for this question to work. And now it's really nice. We can actually just divide by 9, and we get that 10 over 9. And between 10 over 9 and 19 over 9, we have B minus C. And the reason this is so nice is because 10 over 9, well, that's 9 over 9 plus a 9th. So that's a little bit bigger than 1. In fact, it's actually 1.11 or so. 1.111 repeating. This here is 18. This here is 18 over 9 plus 1 over 9. So that's going to be, well, we have B minus C, and then this number here is going to be a little bit bigger than 2. It's going to be about 2.11. So then, if B is a whole number and C is a whole number, B minus C is obviously a whole number, and this whole number is between 1.11 and 2.11. But there is only one whole number that's between 1.11 and 2.11, and that number is 2. So we actually know from this that B minus C is equal to 2. And that's pretty handy because if we take our equation for D here, D is just equal to minus 10 plus 9 times B minus C if you factor out the 9. And this here is equal to 2. So D is actually equal to minus 10 plus 9 times 2, which is 18. Minus 10 plus 18 is 8. So it turns out that if A is equal to 1, D has to be equal to 8, and the difference between the middle two digits is 2. So now we know everything we need to know, and we can just choose values for B and C such that this equation is true, and we get all our peculiar numbers. So let's do that. So I've just written it out here. We know what D is. Well, this is the expression we had for D, and we know if A is 1, then D is 8, and B minus C is 2. I'm just going to solve this for C, and you'll see why now in a second. C will be B minus 2. And the reason I'm solving for C, you could have solved for B, is just, it makes more sense because we're going from left to right. If we choose B, then solve for C, it just makes more sense for the presentation of the video. So we can actually just write out all the peculiar numbers. So I'll start over here. We start off with a 1, obviously. And then what are the middle digits going to be? Well, let's take B equals 0. Well, we can't actually, because if B was 0, C would be minus 2. So the first number we can choose is B equals 2, because then C is 0, and that's allowed. So we have 1, 2, and then if B is 2, C is 0. So we have 1, 2, 0, 8 as the very first peculiar number, at least 4 digits. Because 12 plus 8 gives us 20. Perfect. So again, we can start with 1, and then if B is 3, C will be 1. So 1, 3, 1, 8. 13 plus 18, 31. Good. So I'm just going to keep doing this for all the numbers. You can see this second digit is increasing by 1, and so is the third, which makes sense because of this linear relationship. So if one goes up, the other goes up. So next one will be 1, 4, 2, 8. Then we'll have 1, 5, 3, 8. 1, 6, 4, 8. 1, 7, 5, 8. 1, 8, 6, 8. And of course, the one we were thinking about, 1978. So we've answered the question, what's the one that comes before 1978? It's clearly 1868. Now, what's the one that comes after? So you can actually use a very similar method, and I'd encourage you to do this rather than me doing it. That tells you if A is equal to 2, and you go through the same method, you'll find that D is equal to 7, and that B minus C is equal to 3. So notice this number's just gone down by 1, this number's gone up by 1. That's what I mean by there's a weird pattern in these peculiar numbers, because now we can actually just go on to the next ones. So again, this is going to be C is B minus 3. And then we can just keep going. So we're going to start off with 2. And then if B is 3, again, we're going to have to start at 3 because we don't really have any other option. Because C can't be negative. So if B is 3, we'll have 2, 3, then C will be 0, and we have 8. And then 23, or sorry, the last number is 7, as I said, when A is 2. And then 23 plus 07 is 30. So that's our first peculiar number starting with 2, and it's the one after 1978. We can keep going if we want. We'll have 2, 4, 1, 7, 2, 5, 2, 7, 2, 6, 3, 7, and I'll just go to the end. 2, 7, 4, 7, 2, 8, 5, 7, and 2, 9, 6, 7. So that's all the ones starting with 2. And you'll notice there's one less, actually, than there were. So the one starting with 1, we have 6, 8. Here we have only 7. And the reason for that is because here we're forced to start at 3 instead of starting at 2 like we did over here. So as you can imagine, as you get bigger, the digits in the peculiar numbers actually the number of peculiar numbers actually gets smaller. And something really interesting happens when you get to 9. Before I get on to that, though, I'd like to say if you can think of any intuitive reason, like just, oh yeah, that makes sense, rather than, oh, the maths works, or a visual reason, I'd be really interested. I've tried to come up with one and I just haven't been able to. So the reason that A equals 9 is so interesting is because if A is 9, then D is going to be minus 90 plus 9B minus 9C. And you'll notice these all have a 9 in common. So when we divided across by 9 earlier, the trick was that we got a number slightly bigger than an integer. But here when we divide by 9, we're actually going to get a whole number because 90 is divisible by 9. So we can see what happens now. So we'll have 0. So we'll have 0. And then we're going to have D is in the middle, which is minus 90 plus 9B minus 9C. And that's so it's between 0 and 9. Now if we add 90 to every side, we get 90. And then we have 9B minus 9C. And then we have 99. And then now when we divide across by 9, what we get is we get 10. And then we have B minus C, and then we have 11. Or it could be equal to 11. So here, B minus C could be 10. It's not both at the same time. But the thing is, neither of these solutions actually work anyway, because if these are positive numbers, and they're between 0 and 9, well, the biggest B could be is 9, and when we subtract even 0, we're going to get 9. It's not possible to get 10 out of this. Same for 11. So it doesn't actually matter because there actually are no peculiar numbers, at least 4 digits, that start with 9. And again, is there a visual reason for this? Is there an intuitive reason? Instead of just seeing that the maths works, is there like, oh yeah, that makes sense? I'd be really interested. You could try to extend this, see what happens when you look at the 6-digit peculiar numbers, 8 digits, as many digits as you want, see if there's a pattern. But I just thought it was really interesting, and it'd be even more interesting if there was an intuitive reason for why this weird pattern happens, where the first digit and the last digit are connected together, and so are the middle 2 digits. So yeah, I just thought this was a really interesting question. Let me know what you thought, and yeah, that's it. And if we look for interesting patterns in the peculiar numbers, we can kind of find some. So here's all the peculiar numbers. The ones in yellow are prime numbers. Doesn't really seem to be anything there. Down here I have the count of how many peculiar numbers start with each digit. So 19 start with 0, 8 start with 1, and then it gradually tapers off. Because of that, remember that relationship that b minus c equals some number, and then that number kept getting bigger, so it wasn't possible to get them as many numbers as they got bigger. And then the only kind of interesting thing I could find is if you find the sum or the average of each one's, depending on the leading digit, and you graph them, it looks like this. It's like roughly a normal distribution. And you can also notice that, like, for example, if you look at the green line and the orange line, this kind of cyan line is roughly in the middle. If you look at the yellow one and the green one, this bright blue one's roughly in the middle. If you look at the red one and the yellow one, this pink one's roughly in the middle. And it just seems like there's something interesting going on there. But I don't really know. Maybe have a look into it. And yeah, it's just interesting.